The International Network of Algerian Scientists, INAS, is a nonprofit organization founded in 2016 by Algerian academics and professionals residing in the USA. The motivation is to pay back the homeland and help elevate the level of education in Algeria. INAS's mission is to network Algerian competencies worldwide with counterparts in Algeria. Among its activities, INAS has organized a significant conference that took place outside of Washington, D.C., USA in 2019. The conferees identified several need areas in Algeria and agreed to work on 10 different projects covering areas ranging from education, healthcare, to agriculture and ecotourism, to name a few. The work is ongoing and progressing. INAS is adopting the most contemporary and proven scientific methods to address these issues. INAS's humble beginnings included a few members. Today, it accounts for hundreds of able Algerians from the world over. Their goal is to participate in the rebuilding process of our new Algeria. These able and proud Algerians combine diversity and expertise with benevolence to set a path for a bright future in Algeria. INAS uses a top technology platform to allow members to collaborate and exchange knowledge. As an organization, INAS has different departments that ensure professional support to all its members, projects, and events. We welcome all Algerian competencies worldwide to join us in our noble mission. Algeria is bigger than all of us. Let's stand up and be counted today.
All right, good afternoon, everyone. Thank you very much for joining us in another live with Project Earthquake Hazard Mitigation. My name is Mohamed Amrouche. I'm the project leader, and in this project, we are trying to build and share science among the population on what's going on earthquake hazard research, and try to raise the awareness level about living in an earthquake-prone area like in our country, in Algeria. So in this month, we are very pleased and honored to have Dr. John Douglas, who accepted to kindly share with us his expertise. Good afternoon, Dr. John. Thank you very much for accepting our request.
Okay, thanks for the invitation.
Thank you. So let me just quickly introduce you to our audience. So Dr. John Douglas completed a PhD in engineering seismology in 2001 at the Imperial College of London, following 2.5 years of a postdoc research as a research associate at the Imperial College. He was a senior engineer seismologist at BRGM, French Geological Survey, from 2004 until 2015, during which time has involved in research, public service, and commercial project. He was also a visiting professor at the Earthquake Engineering Research Center in the University of Iceland from 2009 to 2014. Today, Dr. John Douglas is a senior lecturer at the University of Strathclyde in the Center of Intelligence Infrastructure with the Department of Civil and Environmental Engineering. His principal research interests are improving hazard and risk evaluation for natural perils, in particular earthquakes, through various knowledge exchange activities, and he seeks to apply many skills on this field. And today we are very pleased to have Dr. John Douglas introducing the estimation of earthquake ground motion, backgrounds, methods, and challenges. I hope I didn't miss anything, Dr. John.
No, it's very good. Thanks very much. Yeah.
Thank you very much. So please, I can share your screen now. We can see your slides, and the floor is yours.
Okay. Well, thanks, Mohamed. So thanks again for the invitation to share with your audience a sort of summary of the field. So I'm going to begin with a bit of background to the topic, and then I'll move on to a sort of discussion of some methods and then the challenges which we're trying to address at the moment. Okay, so first of all, just to remind everybody about the importance of earthquakes. So this is a photo taken from the central Italy earthquake of 2016. So obviously, unfortunately, this type of scene is quite common. One of the things I want to point out from this picture is the fact that we've got very different behavior of the structures. So we have the building in sort of orange-red color. It appears to be undamaged by this earthquake, and yet next to it there are buildings which are completely destroyed. The shaking that such buildings withstood within this that suffered during this earthquake at this location would be exactly the same because they're very close together. And yet some buildings withstood this shaking, such as the Orange building, and some were completely flattened. So this is obviously shows that earthquakes can be resisted if their buildings are designed correctly. And hence this is important to be able to understand what shaking is likely in the future and be able to design structures to withstand them. So today's talk is really about understanding that levels of shaking that could occur in the future. So generally we talk about seismic risk as a combination of three factors. One of them is the seismic hazard, one of them is the vulnerability of the structures, and one of them is how many buildings there are, the population that's exposed to those that earthquake. So to have a seismic risk, we need all of these three elements. So seismic risk is really a very multidisciplinary field. We have seismology, engineering, and insurance, and other types of fields involved. And then the seismic risk is really the idea. The decision makers then have to make a judgment about what's the level of seismic risk which is acceptable, and if it's not acceptable, take actions to reduce it. And generally we try to reduce the vulnerability of the structures, or perhaps their exposure, or to take insurance to cover some of the possible consequences. So when I talk about risk, we can talk about a number of different measures. So for example, deaths of people or injuries, damage to structures, disruption to the economy, environmental impact, etc. So many different ways of looking at this risk. So today I'm talking about hazard, but just bear in mind that the other ones are all also important. So generally, when we talk about hazard, we produce maps such as this. So this is an example from a project European project I was involved with almost a decade ago now. This map was published showing, and such maps show areas where the hazard's highest. So for example, in this map along the North Anatolian Fault in Turkey, where there's very deep purple color, in Greece and in parts of Italy, and to areas where there's less seismic hazard. So the UK, northern France, northern Germany, etc. So such maps are very useful for designers to know what type of shaking their structures could be subjected to. So when I talk about seismic hazard, I talk about two aspects of the problem. So what we're trying to do is we're trying to determine the nature and intensity of ground motion. So this is generally considered earthquake shaking that could be generated at a site by a future earthquake. So we split this up into two parts. One of them is what's the probability of a given earthquake occurring on a given fault? And then the second part is what's the expected ground motion at a site, assuming the occurrence of that earthquake. So one of them is modeled using what's called a seismic source model, and one of them is what's called a ground motion model. And today I'm going to be talking about the ground motion models. So generally, we express seismic hazard in two different manners. One of them could be the actual shaking that could occur in terms of the acceleration with respect to time. So this is the seismogram shown on the left-hand side. Also, we could, more commonly, we could actually just try to characterize it in terms of a few simple parameters. So the most well-known of these is what's called peak ground acceleration, or PGA, which is simply the maximum acceleration that occurs during the earthquake. We could also talk about response spectra. I'm going to talk about, explain a little bit more about what they are in a minute, but these are simply how a simple model of a structure behaves to that shaking in terms of, so the acceleration that the structure is trying to withstand. And in terms of probability, what we're trying to do is we're trying to express the annual frequency of exceedance of a particular ground motion level. And we can compose that into two parts. the annual rate of earthquakes. So, how often do certain earthquakes occur? And then the probability of shaking that will occur when that earthquake happens. And as I said, what we're trying to do is we're trying to pass this information onto earthquake engineering or insurance, for example, and so they can assess the risk and then understand how to reduce that risk if possible. So now a little bit more about how we express earthquake shaking. So generally, we would ideally like to give a seismogram. So commonly these are known as strong motion records in engineering seismology. So an example is shown at the top here, where you've got the shaking which occurred, and this is in seconds. So the shaking in strong earthquakes is very short, generally 5, 10, 15 seconds. But the shaking levels are very intense. They could be up to, say, for example, 2G, which is two times the gravitational force horizontally. It's a very strong shaking that can occur. We could also express them in terms of, say, velocity or displacement, which are shown at the bottom of this slide. So PGA, even though it's commonly reported, you'll hear a lot of engineering seismologists talk about PGA. It's not as itself a very good measure of earthquake shaking. So this is a figure which is now quite old, but it's very telling in the sense that you can have many different earthquakes which all have the same PGA level, but they're shaking, the actual shaking in terms of the time history is very different. So PGA doesn't fully characterize earthquake shaking. So a better measure is what's called a response spectra. So this figure here tries to explain this. So I'm going to talk through it now. So if you have different types of structures, so at the top we have, say, a long period bridge. So for example, a suspension bridge. Then we could have maybe a tool structure, or even at the bottom some piping system, for example, in a factory or something. Each of these will have a particular natural frequency which it tries to oscillate at. If we subject the ground shaking, so shown in the bottom right-hand corner, to this to a model of each of these structures, the structure will pick out the different frequencies within the shaking. And this is shown here. So this is how the structure responds to that shaking level. And then if we plot, for example, the maximum, say, displacement that the structure withstands, or the maximum acceleration which it's subjected to, and then plot them on a graph, you get what's called a response spectra. So you can see that the structures behave very differently to the shaking depending on their natural frequency or natural period of oscillation. So that's a very important concept, the response spectra in earthquake engineering. So how do we go about predicting the shaking in future earthquakes? So the key data that we need are actual observations from previous earthquakes. So over the last almost 100 years, since the early 1930s, strong earthquakes have been recorded by instruments around the world. So these are what's commonly known as strong motion instruments or accelerographs. So in the past, until probably about 20 years ago, almost all records were recorded on analog instruments. So these recorded on film or paper, and then the recording had to be digitized and to be used within engineering. So it could be actually, calculations could be made with it. In the last 30 years or so, there's been a move towards fully digital instruments. So these record actually digitally, and then you no longer need to digitize the records. So nowadays, I think pretty much all instruments are fully digital. And so the graph in the middle of the this slide shows you a database of strong motion records from all around the world. Each of the dots is an actual record, so it gives the distance from the earthquake and the magnitude that caused that recording. As you can see, there's many thousands of records now in the databases, and they cover a wide range of magnitudes and a wide range of distances. So obviously, most of these have been recorded in areas such as California, Japan, Italy, Algeria, Turkey, etc., where their earthquakes occur very frequently, and hence they've contributed to the database. And with the move to digital instruments, there's a very rapid collection of new data. Roughly every 4 years, the number of records increases, it doubles. So one of the things you can see on this graph is that despite these improvements in networks, there is still a lack of data from very large earthquakes and very short distances. So this is where there's quite a lot of uncertainty in what the shaking would be in a future earthquake. So there are a number of different databases now available online. So there's some logos from a few of them, which you can freely access the data and download it for research or industrial projects, for example. So now I'm going to talk a bit about the methods. So we've talked now about why we need these, why we need to make predictions of shaking and future earthquakes and what data is available. Now I'm going to talk about how we actually go about this. So today I'm going to be talking about what are called ground motion prediction equations, or GMPEs, also called ground motion models, or in the past often referred to as strong motion attenuation relations. So what these are is relatively straightforward to explain. What they are an equation which gives us a measure of the strong shaking. So in terms of what's called an intensity measure or strong motion parameter, such as peak ground acceleration. And this is a function then of, for example, the moment magnitude of the earthquake, the distance from the earthquake source to the site, and then you take your database of strong motion records, such as shown on the previous slides, and you do a regression analysis. So what this means is a curve fitting. So you fit the model, the equation, to the available data. And you get a set of coefficients so that model then best fits the available data. Recently, there's been a move towards perhaps applying some sort of constraints so that the predictions correspond to the sort of understanding, our physical understanding of earthquake shaking. But there's still a need for data to actually calibrate these models. So once we have our equation, we can then use it to predict what's the median ground shaking given a certain magnitude and given a certain distance. So this is shown here for this equation. So you can see that as the ground, the magnitude increases, as expected, the PGA increases, and as the distance increases, the PGA decreases. So as we get further away from the earthquake source, the shaking drops off rapidly. So this is not the only approach that's possible. So this diagram here tries to summarize the different approaches which are available. So we started developing empirical ground motion models, GMPEs, in the 1960s, and they've been derived until the present day. And they're still really the basis of almost all hazard assessments. And because they have a number of advantages in the fact that they're based on data that's recorded, and they can allow us to predict the median, but also how variable that median is. I'm going to talk a bit about that in a minute. But there are many other methods, and in the last decades, there have been approaches based on physical simulations of earthquake shaking. So using such things as the finite element method or spectra elements or other physics-based approaches. And these are useful where we don't have data, or we have data only from small earthquakes and we need to simulate shaking from larger earthquakes. So as I said, the first models were derived in the 1960s, and since then there's been many hundreds of models being published. So this is a figure taken from my website, which you can see the address at the bottom, where I try to keep a record of all the models that have been published, all the GMPs that have been published. So roughly somewhere between 10 and 20 models are published annually, and hence now in the compendium that I collect, there's over 500 models have been published. So all of these have tried to predict a dependent variable. So, for example, peak ground acceleration based on a number of independent variables. So these try to characterize the earthquake source, the travel path from the earthquake source, i.e. the fault, to the site, and then information about the site itself that recorded the shaking. So the earthquake source we characterize using magnitude, so an estimate of the size of the earthquake. We also consider perhaps the focal mechanism, so whether it's a strike slip earthquake, a reverse faulting earthquake, a normal faulting earthquake, etc. Perhaps a consideration of how deep that earthquake is, and perhaps whether it's a main shock or an aftershock. That they're the main characteristics of the earthquake source which are used in these models. The travel path, the important information is how far the site is away from the earthquake source, so the distance. Also, perhaps whether the site is on the hanging wall of the fault or on the footwall. Which region the earthquake occurred in. So does it occur in a stable area or a very active area, etc.? And then the earthquake, the site of the where the earthquake was recorded, information about how soft the soil is underneath that site is very important, and also how deep the sediments are until you get to the bedrock layer. So when you're deriving such models, one of the key questions which you have to answer when collecting together the data is, have strong motion data a nationality? So should we be deriving a model, for example, for Algeria specifically, or Italy specifically, or Japan, etc.? So this is one of the key questions which you have to have an answer for when deriving such models. So in the literature, you'll find a model, for example, derived for Italy using only Italian data. I'm going to talk a little bit about in a minute why this is a bit of a problem, and the fact that we don't have that much data that we can allow us to make such decisions. So a more rational way of doing this is to actually consider tectonics. So I'm going to talk a bit about that in the following slide. But in this slide, what I'm showing is the fact that we can't really rely on nationalistic viewpoints when deriving such models. So what we did for this analysis is we looked at how often earthquakes occur in different countries, and then we assumed that we had a very dense strong motion network recording the earthquakes. And if we needed, for example, 50 large earthquakes to derive a ground motion model, we would have to wait only perhaps 7 years in Japan, because we have a large number of earthquakes that occur, perhaps only 7 years to be able to drive a GMPE. If we went to, say, Italy, we might only have to wait 31 years. So this is feasible given the length of time that strong motion networks have been operating. But if we looked at, for example, Spain, France, or even the UK, we'd have to wait many hundreds of years to actually have sufficient data. So this shows you the fact that we really need multinational databases. It's much better to consider all the data that's available and then use those to derive much more reliable models. So the way this is commonly done these days is, rather than look at it in a nationalistic way, we look at it in terms of tectonics. So what's commonly done is we derive a model, for example, where all the data from the blue areas, so these are the sort of most active areas within Europe and surrounding areas, are combined together to derive a model for those areas. We'd also derive a model, for example, for the red areas and then the sort of grey areas as well, separately, because there's tectonic reasons why the ground motion models might be different in those regions. So now I'm going to talk a little bit more about these independent variables. So we've mentioned distance before, but when we're talking about distance, we need to consider the fact that the earthquake fault is actually not a point source. So generally, when we hear on the news, for example, we hear about the epicenter of the earthquake. But the epicenter is just a single point on the Earth's surface where the earthquake rupture started. But when you're very close to an earthquake, we need to consider the fact that the fault that ruptured in that earthquake could be many tens, even hundreds of kilometers long. So the size of the fault is a function of the magnitude of the earthquake. So the larger the magnitude, the larger the fault. So the 2004 earthquake off the coast of Indonesia that caused the big tsunami, that was many thousands of kilometers long that ruptured during that earthquake, because given so big, what's the large size of the earthquake. So if we're very close to the earthquake source, we shouldn't use the distance to the epicentral distance. We should use a measure which accounts for the distance to the fault. So there's two different measures which are commonly used. One of them is just called the rupture distance, and that's simply the shortest distance to the fault. The other is what's called the Joyner-Bore distance, after the people who proposed it, or the distance to the surface projection of the rupture. So this is basically you project the zone of rupture onto the surface and you measure the distance horizontally. So as mentioned earlier, when we go further away from the earthquake, the fault, the earthquake source, the decay of ground motions is rapid. So this is a figure demonstrating this for some very large earthquakes. And as you can see, there's a factor of very many factors of decrease as the distance increases. So then we talk about the magnitude of the earthquake. So the effect of magnitude on earthquake shaking is that as the magnitude increases, in general, the amplitudes of the shaking also increase. So this is demonstrated in this figure here. The other thing you can see is as the magnitude increases, the duration of the shaking also increases. You can also consider this effect on the spectra, so the response spectra that occurs. So for small earthquakes, which are the thin lines at the bottom here, the thin solid lines, you have a certain spectrum. If the magnitude increases, the spectral content at longer periods also increases. And so you get a larger spectrum, both in terms of amplitude and also in terms of frequency content to the lower frequencies or the longer periods. So now we also talk about the faulting mechanism or the focal mechanism. So this can also have an impact on earthquake shaking. So this figure here tries to demonstrate the impact of faulting mechanism on earthquake ground motions in terms of, again, response spectra. So as I mentioned, you normally consider 3 different types of earthquake: strike slip, reverse, and normal faulting. So on the left-hand side, we have the ratio between strong ground motions in reverse faulting earthquakes to strike slip earthquakes. So if you look at the y-axis on this graph, you can see that in reverse faulting earthquakes, in general, ground motions are slightly higher, perhaps by 10-20% than they are in strike slip earthquakes. But there's considerable uncertainty in that observation. In contrast, between normal and strike slip earthquakes, you find that normal faulting earthquakes, on average, the ground motions perhaps are slightly lower than they are in strike slip earthquakes, but perhaps by 10-20%. But again, there's quite considerable uncertainty in that observation. And then the final part of the puzzle, which I'm going to talk about, is site effects. So as has been commonly observed in hundreds of earthquakes, low velocity soil layers can amplify greatly strong ground motions. So this is due to the fact that there's what's called an impedance contrast between the bedrock and the softer layers at the top, which amplifies the motions. You can also get resonance in those softer layers. And you can also get the effect of surface waves being generated at the edges of sedimentary basins, which can further amplify the particularly long period ground motions. So because of this, we basically have been including site terms within GMPEs pretty much since they first started being derived in the mid-1970s. And the most common way this is done is what's called the use of VS30. So this is using the average shear wave velocity in the top 30 meters as a measure of how soft the sedimentary layers are, or the rock layers. So at the bottom of this, slide, there's a graph showing the factor between ground motions on soft soil, so characterized by VS30 of perhaps 200 meters per second. So this is very soft soil, to rock. So this is a VS30 of around 1,000 meters per second. So as you can see, the ratio here can go up to perhaps a factor of 7 at long spectral periods, so around 2 seconds. But it's not as strong at the shorter spectral periods. So this is very important for long period structures such as skyscrapers or long bridges, and perhaps not as important for ordinary structures, ordinary houses, for example. So now I'm just going to compare between an old and a new GMPE. So for the old one, I'm showing the original GMPE, so not called a GMPE at the time, but by Esteve and Rosenbluth from 1964. So this equation was derived based on only 46 records, and they only had 3 coefficients within this equation. So you can see them here as C, alpha, and beta. And they basically just used whatever data was available, and they did a regression analysis. And it's quite a very simple equation based on pretty much whatever was available at the time. Nowadays, models are much more complicated. So this is an example from a recent study called NGA West 2, where they derived a number of highly sophisticated ground motion prediction equations including this one here, which you can see is incredibly complicated in terms of the function which is being is used. They've used over 15,000 records, and there are 40 coefficients within this model. And rather than just use whatever data was available, they carefully selected the data. They checked all the data carefully before using it to derive the model. And then they looked at various aspects of the model to make sure that it's applicable for as many different situations as possible. So generally, models in the last decades or so are somewhere between these two, more towards the right-hand side than the left-hand side. They're becoming more and more sophisticated, and more data is being used. So now I'm going to talk a little bit about some of the challenges in using these models and that we're trying to address in current research. Okay, so the first of all, we're going to talk a bit about uncertainties. So I'm going to talk about two different types of uncertainty. One of them is called epistemic uncertainty. So to explain what this is, this figure shows the recordings, the peak ground accelerations recorded in the Northridge 1994 earthquake, which was a large earthquake that occurred in California. So each of these symbols, so the triangles and the squares and the circles, are recorded peak ground accelerations during this earthquake, quite close to the earthquake fault. So if you had that data, you could fit multiple GMPEs through the data. So these are signified by these colored lines. Each of those curves is almost equally likely to be the correct curve for that data. So this indicates what's called epistemic uncertainty. Because you don't know which of those models is the correct one, you actually, if you're using those models to predict future shaking, you can have quite a significant difference in the predictions. So if you compare, for example, the yellow curve to the red curve. So that's what's called epistemic uncertainty. The other concept is called Allitory variability. And in this, what you do is you take one of those curves, say, for example, the red curve, and you compute the residuals. So the difference between the, say, the square and the line itself. So the difference between the observed and the predicted ground shaking. So that's what's called Allitory variability. And that shows you that there's a considerable scatter around that median prediction. So for a future earthquake, you need to account for the epistemic uncertainty in what's the median and the variability, Allitory variability in whether is the shaking going to be higher than that median or lower than that median. So what we normally do is we use what's called logic trees. I'm going to talk about those in a minute to handle the epistemic uncertainty. And we account for the Allitory variability in terms of, for example, the standard deviation of the GMPE, which we account for using generally what's called a log normal distribution. So another illustration of epistemic uncertainty. So if we take all the GMPs in the literature and we predict the median shaking from each of those for a particular scenario, we can see how uncertain the predictions are. So if we consider a scenario magnitude 6 strike slip earthquake at 20 kilometers on stiff soil, we get a graph like this. So this is against the date where the GMP was published. If we then wanted to make a prediction for that scenario, we could either choose, for example, this model at the bottom here, which gives a prediction of, say, 0.03 G, or the one at the top, which is perhaps a factor of 20 times higher. So obviously, making these different predictions has great engineering implications. It's much easier to design a structure to withstand 0.03 G than it is to construct one to withstand a shaking 20 times larger. So we really need to know which of these dots is the correct estimate of the median PGA. So to go about this, one of the ways is we start with the all the GMPs in the literature, so the 500 plus models which I talked about earlier, and then we can apply a sequence of quality assurance criteria. So I was involved in a paper now in 2010 where we came up with a set of questions which you could ask to try to eliminate those models which are not appropriate for your study. You can also test your models against any data that's available. So this is an example from a study which I conducted for the French Antilles in the Caribbean, where we looked at a series of GMPs and tested them against data that was available. And then you can rank them, A to D, for example, and how good they match the data. So this is an example here that the Cano et al. Model is the most appropriate for this based on this data. The problem with this is that the scenarios which you're most interested in, so the larger magnitudes, the shorter distances, they're not generally very well sampled within the databases that are available. So you're not sure that if it predicts well for the small earthquakes, is it going to predict well for the larger earthquakes? So just to summarize, what we generally do when we're trying to select a GMPE or a series of GMPs for a study, we look at the literature, look at what models are available. Then we apply some judgment to those. Which one of these are from similar tectonic environments? They use a sufficient amount of data. They have certain characteristics that we want the model to have, etc. Then you test those models against any data that was available, and then you select from all those hundreds of models, say a handful of models which are the appropriate ones. So these are the ones that are colored here in red, blue, and green. And then we apply what Warren Buffett does for stocks and shares. So Warren Buffett, those of you who don't know him, he's a famous shareholder, and he buys and sells stocks and shares. And what he says is diversification is a protection against ignorance. So we don't know which of those say 3 models in this case is the most appropriate for our study. We're ignorant of that information. So we diversify. So we select a number of them, and then we give them certain weights depending on how good they are for the location. This is based generally on judgment. So here, this is an example from the SHARE project, which I mentioned earlier, where we selected 4 ground motion prediction equations for Europe, and we gave them different weights. So I'm not going to go into the details here, but for example, 2 of the models we gave 0.35 weight because we thought they were the most appropriate. Another one we gave 0.2, and one we gave 0.1. And that sort of, we're saying we're ignorant about which of those is the best, and we're diversifying our portfolio in this case. He also says, though, it makes little sense if you know what you're doing. So he thinks that he knows which stocks and shares are the best. So he doesn't really perhaps believe completely in diversification. And perhaps there are better ways of doing this, which I'm going to talk a bit about in a while. The other aspect, the Allitory variability. So this is the variability in a given ground motion record. This is also a very important aspect of ground motion prediction equations. This is actually not really been decreasing with time. So we get more and more data. The data is equally variable as the older data. Even though we're doing much more sophisticated models, we don't actually have much decrease in the sigma, the standard deviation of the GMPE. So this is shown in this figure here. So one of the questions is, what is the correct value of sigma? So this is a very important question to answer, because it can have very large implications for the shaking that we could predict for a future earthquake. So this is indicated by this graph here. So I'm not going to go into details about hazard curves here, but just to say that if we were, say, doing seismic hazard assessment for a nuclear power plant, so as some of the consultancy that I do, I'm involved in seismic hazard assessments for nuclear power plants, and often we're interested in very low annual frequency exceedance, so perhaps 10 to the -4. So we're interested in that low annual frequency of exceedance. The value of sigma that we use in the model can have a very big impact. So if we had a model which had a sigma, in this case, of 0.19, so this is in log to the base 10, we'd have a certain PGA value of, say, 1G. If we had a GMPE where the sigma was 0.27, so it doesn't appear very different, the actual predicted ground motions for that annual frequency exceedance could be a factor of 1.7 times higher. So obviously that can have big implications for the design of a nuclear power plant. So the question is, what value of sigma is the correct one? So this is one of the research topics which is very active in the currently. So now I'm going to try to explain the trade-off between epistemic uncertainty and Alliatory variability. So imagine that we're trying to do a seismic hazard assessment for this fictive isle. So the green blob that's on the screen here. So we want to design a structure at the point here in a star. So what is the design PGA for that location? So one way of doing it is to use the strong motion database that I mentioned at the start. So these thousands of ground motion records, and simply do an average of all of the observed PGAs from that strong motion database. In that sense, we would be we'd have lots of Allitory variability because we're mixing up lots of different magnitudes, lots of different distances, lots of different site conditions, etc. We'd also have some epistemic uncertainties because we don't know that that database is representative of this fictive island we're trying to consider. So there might be different tectonics between the database that's available and the tectonics of the this location. So then we might think, what I'll do is I'll use a GMPE. So I'll use one of these models which have been proposed in the literature that accounts for, say, the difference in magnitudes, difference in distances, etc. So now we're not considering these as Allitory variabilities, but they're actually epistemic uncertainties because we need to know what's the magnitude of the different earthquakes which could affect my site. How distant are they from the site? What are the shear wave velocities of them, etc. So they're now on the epistemic uncertainty side. So then I might think, well, what I can do is I can use a more complex GMPE, which accounts for other factors. So these now drop off the left-hand side, but we need to consider them as epistemic uncertainties on the right-hand side because we need to consider all possible values of those which are appropriate for our site. And then you can maybe use simulations or more complex ground motion prediction equation, and they remove from the left-hand side and they go to the right-hand side. So I like to summarize this as there's no such thing as a free lunch. You can't have no epistemic uncertainty and no Allitory variability. You have to have, well, basically, if you move one from one side, it appears on the other side. So now I'm going to talk a little bit about the concept of what's called a backbone model. So rather than use these multiple GMPEs and hope that by weighting them, you account for the uncertainty, you have a more transparent way of capturing this uncertainty. So what you do in a multiple GMPE approach, as I've mentioned before, you have the, say, 3 ground motion models from the literature, and you can plot them such as this. So this is for a single magnitude and a suite of distances. So that would be the multiple GMPE approach. But there you can see that there's uncertainty at the shorter distances and the longer distances, but at a certain distance, the models might actually overlap. So that means that you're basically capturing no uncertainty at that single distance. So that's probably not a true reflection of your knowledge about the ground motions in this case. If you don't know something here, you probably don't know it here either. So what's done in the backbone approach is you select the best model you can from all of the available ones, and then you scale it by a certain factor, which could be just a single factor for every magnitude and every distance, and that or it could be more complicated than that, and that's more of a transparent way of capturing uncertainty. It captures the fact that you don't know which model's the correct one, but you don't account for that by selecting a suite of different ground motion models. You select one and you scale it. So this has a number of advantages, and the main one is really you're being transparent about the level of uncertainty that you're applying, that you believe to be correct for your location. So now I'm going to talk a little bit about so that's really epistemic uncertainty and how it's best to capture that. Now I'm going to talk about Allitory variability and how you can capture this in a better way. So what we would like if we were designing, for example, a nuclear power plant for a particular site, ideally what we'd like is we'd like recordings from all the different earthquakes which could affect our site. So these are the stars in this case. But we don't have the luxury of waiting many centuries to collect this data. We need to, say, start the construction next year, for example. So what is done when we're deriving GMPEs, what we do is we select, we have data from many different sites, but with fewer earthquakes. And then in physics, there's a concept called the ergodic assumption. And so what you do is you replace time, the fact we don't have centuries to wait, by space, the fact that we can select data from many different regions, many different locations. So we do this and we make the ergodic assumption, and we can then derive our GMPE. But by making this, you're actually accounting for slightly too much variability because you're combining data from many different sites. So in the last decade or so, there's been a move towards what's called non-ergodic hazard or partially non-ergodic hazard. And so what this means is that you look at the variability in ground shaking at a particular individual sites. So you've removed the fact that you're combining lots of different sites together. So that reduces the variability. And you can then use what's called single station sigma, so single station standard deviation of the GMPE. And then you adjust those predictions for those sites to the site of interest. So those models can then account for regionality due to repeatable site, path, and source effects. So as I said, this concept has been started maybe 15, 20 years ago, and there's been lots of work on this in the last decade. So I'm just going to show two examples. So one of them is from California. So there was a study that was done in 2016 where they derived basically multiple GMPEs for California. And they have coefficients that then vary for depending on their location. So these betas, beta 0, beta 3, etc., are coefficients within the GMPE. So this can account then for the differences in ground motions between, say, Northern California and Southern California. There's also been lots of work done in Europe on this. So a recent study by Kother et al., where they derived a GMP which accounts for regional differences in terms of the source effects and the path effects. So the areas in the sort of reds act similarly, and those in blues are also similar, for example. So two different approaches, but with the same goal of moving towards non-ergodic models to avoid over inflated values of Allitory variability. There's also been a move in the last decade or so towards non-parametric models. So as I said at the beginning, generally what you do is you assume a functional form and then you fit that functional form to the data. But you can also not assume a functional form, but allow the data to actually shape the ground motion model. So there's been lots of work and many different approaches of machine learning, artificial intelligence towards this idea. So as an example, I was involved in a study where a number of different, 5 different models were derived using very similar sets of data. And 2 of those models were actually non-parametric. So these are the red and the blue curves in the figures on the right-hand side. So different magnitudes and for different distances. And this study was quite interesting in the sense it showed that such non-parametric models can actually give very similar predictions if the input data is the same as parametric models, so ones with a functional form. One of the issues, though, is when you get to the larger magnitudes and the shorter distances, such models break down because you don't have much data to constrain them. There's also been, as I mentioned at the beginning, some move towards using simulations. So the database that we have available is quite sparse in terms of the largest earthquakes and the shortest distances. There's also not very much data from sites where the soil itself is behaving non-linearly, or from inside sedimentary basins, for example, or from areas such as the UK or Northern Europe, where the tectonics mean that earthquakes are very infrequent, so you don't really have much data, but you might need to do a prediction for very important infrastructure. So in those cases, simulations are very important because they can complement the available recordings and allow you to make much more reliable ground motion models. One of the issues, though, is the fact that the input data to simulations is not completely known. So we don't really know what's the true distribution of those input parameters. So you could be over or underestimating the uncertainty in those simulations, depending on how broad a distribution you put into the simulations of the various inputs. So now I'm going to, just to conclude, I'm going to show an example of the concept of value of information. So this is a topic which I've been, with a PhD student, I'm been working on recently. So this figure is a bit tricky to understand, but I'm going to try to explain it by saying that we can move from low certainty on the left-hand side to high certainty on the right-hand side for a particular information. So we can consider the x-axis as time. As time increases, our information available increases. And as we can then say how much is a piece of information worth in terms of dollar, for example, or how much decrease do you get in the uncertainty level? So if you had back in the 1930s, when they didn't have any strong motion data, they didn't know anything about what the shaking is during an earthquake. So that first strong motion record is very valuable, and it's got very high monetary value because it decreases the uncertainty by a lot. As you get more and more data, each additional strong motion record is worth less and less because we already have lots of data in the past. So it doesn't decrease as much the uncertainty as the original strong motion record. So if we consider, for example, California, where they've had now almost 100 years of strong motion recordings, perhaps we're getting to the sort of an asymptotic value of the amount of the uncertainty that we have. So we're getting more and more certain, and each additional piece of information doesn't change very much that model. But if we're in an area such as Algeria, where this strong motion network is sparser and hasn't been run for as many years, each additional strong motion record is much more valuable because it allows us to change our models by a lot more because we become more and more certain. So we can, I quite like this quote by Francis Bacon. He says, "Truth is the daughter of time, not of authority." So basically, if somebody in authority says something is true, if they don't have the data or they haven't got the time, they haven't had the time to say whether it's show that it's true, we shouldn't believe them. We should time or data is the path to truth, not being a big authority on the topic. So just to conclude, we derive ground motion models since the 1960s, and there's been many dozens of such models being published every year. And in the literature now, there's many hundreds of models in the literature. Most models these days are becoming more and more reliable as there's more and more data available. But we need to consider the fact there's uncertainty in the median, so epistemic uncertainty, and there's variability in a prediction. Epistemic uncertainty is particularly large where we don't have much data, so we need to account for that uncertainty when making a seismic hazard assessment. There's been a move towards what's called the backbone approach, which has advantages in the fact we're being more transparent about that uncertainty we're capturing. There's also been a lot of work recently on the non-ergodic assumption. So non-ergodic models which capture regionality in ground motions and allow us to reduce the value of sigma that's being used within seismic hazard assessment. Simulations are promising, but they're still not used in practice because of the problem of what's the correct inputs into the simulations. There's potential for artificial intelligence type approaches to derive ground motion models, but these are perhaps not as reliable at the larger magnitudes, shorter distances that are particularly important for seismic hazard assessment. Okay, thanks very much. So I'm happy to answer any questions you may have.
Thank you very much, Dr. John Douglas, for your very interesting lecture. You really helped us to demystify the equations, the ground motion prediction equations, and indeed, it's a very, very, very interesting lectures we had here. You started by covering the very fundamental definitions of the GMPs and their evolution, and discussed the variables of the ground motion, and finally discussed the uncertainties and how quantify them. So I would like to recall our audience that you can ask your questions in the comment sections. We do have few questions here, I see. So let me just pick up a few questions and ask to Dr. John Douglas. First question is there any new contribution of machine learning algorithms using existing seismic catalog to improve GMPs? Yeah, probably some more discussion about non-parametric GMM, probably.
Okay. So should I was just wondering, should I stop sharing my screen?
Sure. You can go. Yeah. Here you go.
How do I? Yeah. Okay. Do I? Is it stopped? No, it hasn't stopped. No, that's it. Okay. All right. So thanks for the question. There's been a lot of work in the last decade really on machine learning. So I'm not completely familiar with all of the different studies, but some of them are very promising in the sense that they can give us much sort of more detailed models, ground motion models, rather than having to assume a functional form. Because then obviously it's quite a simple shape that the predictions have. And we also don't know all the physics. So they allow us to really see what's in the data, perhaps in a better way, maybe than some of the parametric models where we have to assume a functional form, which we don't know. So it gives us some scope there. But the problem is that for the largest magnitude, shortest distance, if you don't have data, the model doesn't really know what to do. So it can lead to probably some erroneous predictions, but it's very useful approach when you have a very rich database. And there's been a lot of good work done on that. Yeah.
Thank you very much. We'll pick up another questions from our audience. This one is from YouTube. How do we measure the size of the fault?
Okay, so generally the fault, the rupture of the fault rupture is measured in terms of the length of the fault. So just from one end to the other, also the width of that fault. So in terms of the how far into the earth it goes. You can also consider the area, for example, of the fault, so the surface area. So generally, the fault rupture is along a plane, so it's not like a volume; it's along a plane. And the rupture starts from the epicenter and propagates along the fault, and maybe that propagation might take 10, 20 seconds for the largest earthquakes. It travels at a very fast speed. The rupture propagation, and then at some point it will stop. Yeah, so the size is important in the sense that if we're looking at GMPEs, it's the distance between the fault and the site which is actually the key thing. It's not where the rupture started, which would be the epicenter. It's really that shortest distance.
Thank you. Okay. Thank you very much for your answer, Doctor. So I will pick up another question from the audience. What about the use of logic tree in Algeria context? Is there example of backbone approaches in the Mediterranean region?
Okay, so I'm not 100% familiar with all of the seismic hazard assessments done for Algeria, but I assume that they've probably used the logic tree multiple GMP approach. The backbone approach has really only been started being used in the last 10 years or so, but one of the recent studies, which it was done in Europe, but possibly they covered Algeria as well, is what's called the European Seismic Hazard Model 2021, I think it might be. And it's only recently been published, and they used a backbone approach in that. So it might be worth having a look at that study. It's one of the most recent studies. If people are interested, I can give the reference. Yeah.
Thank you very much, Professor Doctor. So we will finally take one last questions because we are a little bit running out of time here. So let me just take one question from the audience. Let me check here the questions from our audience. Yeah, thank you very much for the lecture. In site effect studies, what are the limitations of the reference site method and how much is it reliable? I don't know if you are expert on site effect assessment.
So the reference site method, I'm assuming this is you have a recording on rock and you have a recording on soil, for example, and you can look at the difference between the two. So one of the issues is the fact that you would need the reference site and the soil site would need to be quite close together so that you can get a reliable answer. Otherwise, there could be differences in the distance, for example, the magnitude of the earthquakes, etc. So yeah, it's not really an area I know a lot about, but there are other methods to allow you to reduce some of those assumptions.
Yeah, probably combining with the HVSR, H over V spectral ratio, or some other microterm.
Yeah. Okay.
All right. So with that said, I will not hold you much longer, Dr. John Douglas. Thank you very much for today's presentation. I would like to thank our audience also for participating live in our lecture this month. So we just would like to remind you that INAS, International Network of Algerian Scientists, is having an annual scientific conference, and tomorrow we are going to have day 2. So if you have time, please check our INAS web page, and you can see the live of our panelists for tomorrow. Thank you again, Dr. John Douglas, for your time and for your lecture, and really looking forward to see you for another opportunity.
Okay, thanks very much. Okay.
Thank you. Have a good day, and thank you for
all right. Bye.